So object 1 is going to be represented by x11, let's say y11, x21, y21, so on and so forth, xn1, yn1. Object 2 is going to be x12, y12, x22, y22, so on and yn2. So the superscript denotes the object number, right? Subscript denotes the landmark number in that object. In order to compare these two, one way is obviously subtract the two. Okay, when you are subtracting these two, what are you doing? You are comparing the first landmark in the first object with the first landmark of the second object. So if this denotes tip of the nose and this denotes tip of the wing, that's basically comparing apples with oranges, right? So that is what I mean when I say that there has to be a semantic correspondence between the landmark points. So I am comparing the same landmark in this object with the same landmark in the other object. Make sense? Yes. Not only the starting position, but this landmark, whatever it signifies in the object, right? For example, if this is the tip of the right wing, this second point here should also be the tip of the right wing. Okay, and second point is, as we discussed, all the objects must have the same number of landmarks. That is purely a mathematical restriction. Okay. All right. What is the time? Are we running far behind? What is the time now? Okay. Thank you. Okay. Right. So next question is, right, both of them are now vectors in the same vector space. O1, O2, both of them belong to R2n. I can just compute the distance between these two vectors in Rn, right? So of course I cannot draw anything apart from R3, but just assume this is a diagrammatic representation of R2n. So this is O1, this is O2, right? I can compute this distance, the straight line distance between these two vectors, and that is what is shown in the slide. Question is, this distance between the landmark point representation of the objects, can I interpret it as the difference in the shape of these two objects? You can't, right? Anybody who thinks we can? And why can't we interpret this as shape difference? Exactly. So that is what we started out by, right? We defined shape as an information that does not change due to translation, rotation and scaling. That is something that we have not at all factored in over here. Right. So for example, I may have two aircraft images, one is of size 100 cross 100, the other is 1000 cross 1000 pixels. Right. So just imagine I'm just increasing the resolution of the same aircraft image by 10 times. Right. So the object is the same, therefore there is no difference between the shapes of the two objects. But if you just find this distance out, of course you will get some large number. Okay, so before we do this, we need to somehow factor out translation, rotation and scaling. So that process is what is called Procrustes alignment. You may be thinking, what is Procrustes? Alignment, I hope you can understand, but Procrustes, so Procrustes possibly I think is a name of a Greek demon in Greek mythology. Okay, the story is something like Procrustes is supposed to be an innkeeper on some Greek highway, and all his rooms have the beds of the same size. If a traveler came who was too short to fit in the bed, he used to pull them so that the traveler fit exactly into that bed. And if somebody was too long, he would cut off that much portion of the leg so that he exactly fit. And in principle, that is what we are also planning to do with shapes. Okay. Right. So I'm going to stick with complex number representations. Okay. So every landmark will be represented by one complex number. Collection of n landmarks. Right. So if there is an object 1, I will represent all the n landmarks by the notation C1, and C2 denotes the landmarks using n complex numbers of the second object. We want to eliminate any differences between these two landmarks that have arisen due to translation, rotation and scaling. Right? I have sort of repeated this enough number of times. So, before we can compare the landmarks, right, we want to translate C2, we want to rotate C2 and we want to scale C2 so that it becomes as close as possible to C1. Why? No. C, it's not C square, it's C2. Once again, be careful. Maybe. So C1 represents landmarks of one object, C2 represents landmark of the other object. Okay, it's not C square. Okay, perhaps a poor choice of notations, but yeah, now I can't change it anyways. So the idea is, once again, you want to eliminate any differences between these landmark representations that have arisen due to translation, rotation and scaling. So the best way to do away with them is to align these two using these same three set of transformations. Are we all okay? Okay. So how will you, by how much will you translate C2, by what angle will you translate C2 and by what scale will you scale C2? How will you find these transformations? Okay. So, acha. But with one point, how will you find the rotation? So, again, imagine this is some aircraft. This is one point. This is other aircraft. So, then, okay. One of the point. Okay. So what is the distance that you are trying to minimize here? Between what and what? Why only nose? When, so something like this, the nose is in place, right? Hmm. Okay, so no, let's stick with aircraft. So let's say, yeah, something like this. So you're saying the mean has aligned. Then how much will you rotate? Why are you giving importance to the nose? Is that true? I mean, it's not a trivial question or a trivial answer, by the way. Which landmark points? All landmark points. That's different from aligning just the nose. Okay, so think about it. The basic idea is you would want to, okay, let me stick to the same notations C1, C2, Cn. So translate, say rotate and scale C2, so that what should happen? Equal to C1. But can you ensure that it will always be equal to C1? So then what is the next best thing? Minimize the distance. So find the amount of scaling, rotation and translation that we are going to apply to C2, so that the distance between corresponding landmark points are minimized. Okay, all landmarks, not just the nose. Yes. No, how much you want to minimize in the sense the least that you can. There. Sorry? What? Yeah, so that's what I'm saying. So your landmark representation must have semantic correspondence. So if one is an aircraft and another is a car, right, you should not use this. That's fine. I mean, landmark is just a representation and it's your choice, right? You can represent a car with 50. So this thing assumes that you are working with the same kind of objects or objects of the same class. Right. Yes. Threshold for the minimum. I mean, try to get as small as possible. The smallest that you can get is 0. So that is some conclusion that you can make after doing this, not right now. See, right now the difference between landmarks could be large because of translation, rotation, scaling. So after aligning, we will come to the conclusion that whatever is now the difference between the aligned landmarks is due to difference in shape. Okay. Somebody had a question here? Clear. Okay. Yeah, so slightly different notations here. Could you decode what these notations are? Yes. So what is this V times 1? What is it doing? Translated. So by the way, although it's not written, V denotes one complex number. 1 denotes, sorry, all one vector. So V is a complex number. 1 is a vector containing all ones, n ones. So when you multiply V to 1, you will have V at all n entries. So what happens when you subtract V into 1 from C2? From every element of C2, every element of C2 is nothing but a landmark point. So when we subtract the same number from each and every landmark point, what are we doing? Translation, right? So that's translation, right? And of course the unknown, as you can see, is V. Next, what is this e to the j theta doing there? Rotation, right? So what is rotation matrix? So when you apply it, x cos theta minus y sin theta, x sin theta plus y cos theta. Try and see if you will get the same thing when in complex number notation. Or j theta into x plus jy. It's no reason. We could use I as well. Okay, yeah, that's something maybe I should announce. So that's j is square root of minus 1, you're free to use I instead of j. Okay, so when you multiply these two out, you will get this as the real part and this as your imaginary part. Okay. Right. So how are we going to find V, theta and S? Sorry? Right. Okay. One should be a, it is basically a regression problem, yes. How do you solve regression problems? Exactly. So this is an optimization problem, right? Differentiate your cost function, set to 0, you will get the answer. Okay. For V, we will use a slightly simpler strategy. So assume that, as he rightly pointed out, assume that the mean point of both landmarks, set of landmarks, is the origin. Okay, so what does this mean? It's just summation xi plus jyi, I going from 1 to n. 1 y1. And similarly, I going from 1 to n, xi2 plus yi2 is also 0. Okay, what it means is all the landmark points are sort of equally distributed about the origin, whatever. Okay, is a shorter way to write this, which is C1 star denotes complex conjugate. So, if you understand complex or conjugate transpose, sorry, not just complex conjugate, right? So this is a vector in Cn, but it's represented as a column vector. C1 star will be a row vector, and whose entries are complex conjugates of the entries in C1. So this I can write it in a simpler way, this way. Star 1 equals C2 star 1 plus C. Right, I am just adding all points when I am multiplying this row vector with vector 1. Okay, so assume this is the case and then expand this cost function. So how will you expand this? This is basically like norm of a minus b squared, right? So yes, exactly, that's what I want to show, that if this is the case, the v that minimizes that cost function will be 0, which means you don't need to translate. Once this is satisfied. So can someone quickly expand that cost function? So the definition of norm C squared is just C conjugate transpose C, right? Will be the first term. Now just multiply out the entries out. First term, norm C1 squared, right? C1 star C1, that's norm C1 squared. Then the last one, S by the way stands for scaling, so that's a real number. Okay? What is this multiplied by this? So, S squared e raised to minus j theta e raised to j theta is 1. Then this is nothing but the conjugate transpose of this, right? So therefore this is C2 minus V1 norm squared. And what else? this times this and this times this, what will you end up with? 2 times, sorry, norm of C1. But A and B are complex numbers. So no, will not have a norm in it. So C1 star into this and this into C1 together, what will it give you? Okay, observe. So this into C1 is some complex number. What is the relation between this complex number and the complex number that you get by multiplying C1 star to this? Okay, let me S is to minus j theta C2 star minus V star 1 into C1, and the other is S is a real number, E is a complex number, so I can just bring them out. V star C2 minus V1. What is the relation? No, they are just complex conjugates of each other. So when you add only real parts, thank you, to S real part of e raised to j theta C1 star C2 minus V1. Can I erase this now? Now if you look at everything that involves V, right, what do you get when you multiply C1 star to V times 1? Zero. When you expand this, what happens? Second factor. In the same way that we did this, you should be able to do this. What will you get? Be a C2 norm squared, then minus C2 star V1, that is 0, and 1 star, so 1 transpose C2, that would also be 0. Same thing, right? I mean, whether I have a star here or whether I have a transpose here, this will be the same if this is true. So, then what are we left with? Okay. So, what should be the value of V to minimize this? Now, that's an easy question. So, V should be 0. Do you see that? This is absolute value of v squared. That's the only term where v remains. So that this happens. That is exactly what we have concluded, right? So v optimal therefore is 0. What does it mean? By what amount are we translating? No translation. Okay. So that's first thing. So then let's now write the cost function in terms of the remaining variables. C1 squared plus s squared c2 squared minus 2s real part of e to the power j theta c1 star c2. What should be the value of theta? So you want to minimize this with respect to theta. This has no impact. So this is the only term we need to consider. If you want to minimize this term is going to be subtracted from this. So we need to maximize this, right? Theta optimal is arg max of the real part of e to the j theta times the complex number c1 star c2. Now you should be able to tell me quickly what should theta be. Shouldn't be 0 for sure. No. See, forget this. I mean, if this notation is confusing you, this is just one complex number. So just treat it as if it's like a plus jb. And what is e to the power j theta? Right. So let's say this is your real part, this is imaginary part. C1 star, C2 is something like this, let's say. And e to the power j theta will always be a unit magnitude. So what theta will you choose? Of that complex number, are you sure? So you're saying minus. Okay. See, when you multiply two complex numbers, you will get one real part and an imaginary part, right? Obviously. Now, if you can somehow make the product of these two complex numbers itself a real number only, that will be the maximum. So, for what e to the power j theta will this multiplication result in a real number? It has to be the complex conjugate of this complex number just divided by its norm, because you want a unit magnitude complex number. That is e to the power j theta. From this, I hope you can see that theta is argument of the complex number C2 star C1. Argument is tan inverse imaginary by real. Make sense? Yes. No, this has to be C2 star C1. Cannot be C1 star C2. Because, so this is one complex number. Forget the denominator for now, right? If this were to be C1 star C2, this would be just square of that complex number. That would have a real part as well as an imaginary part. You mean the first line here. So V is just one number, right? No, V is one number. To make it into a vector, I am multiplying it into a vector of all ones. So then it doesn't matter whether you multiply it after the vector or before. Right? Okay? Yes. Yes. Hmm. See, please remember C1 and C2 are n-dimensional vectors, but C2 star C1 is just one complex number. Therefore, I am just writing it as the absolute value of that complex number and not norm of that complex vector. Okay, fine. I think I need to speed this up a little. Okay, so what is now the cost function? Assuming we use the optimal value of rotation, what is J of S going to be? What happens here? Just substitute this over here. So you will get agree? Find the value of S. Quick, I mean, now it's just simple differentiation and setting to 0, finally. So, just a minute. S optimal is norm of C2, norm C2 squared. Okay. Fine? Yes. Now, after doing all of this, the difference between the landmark points is what is called the shape difference or the full Procrustes shape distance. That is nothing but you substitute the optimal value of scale here. So that's your C1, C2, or write it using the same notations. What happens if I substitute S optimal here? I hope you see that you're going to get that. This is called the full Procrustes shape distance. One strange thing, try to observe that. What is C1 and what is C2 here in this particular equation? Sorry? List of complex numbers or landmarks. But what sort of landmarks? Aligned or original? Original landmark points. Right. So if I'm interested in computing the shape difference, only the number, then I need not do any of this. This number is directly the difference in the shapes represented by the two landmarks that we have. Geometrically, what this means is, can I erase this off? Okay. We are due for a break. Just give me 5 minutes.